So, what factors determine the magnitude of the energy difference? The energy difference itself is what we refer to as the crystal field splitting energy, and it has a symbol delta. Now, here I have an O next to it because I'm specifically referring to the energy difference in the two levels that is a result of the splitting that happens in octahedral complex. If you have tetrahedral complexes, then it's going to be a different value. For all of the discussion here, I'm going to just focus on octahedral complex. Now, the magnitude of that delta depends on, first, the charge on the metal ion. As you might imagine, if the metal ion has larger charges, that electrostatic repulsion is going to be even more pronounced, so you're going to have a larger delta. The position of the metal ion turns out to matter in the periodic table. If it has a larger shell, meaning that you're lower on the periodic table, higher period, then that's also going to result in larger delta. And lastly is the type of ligand itself. So if you have specific ligands, it might split the energy as a strong field versus some other ligands might split it in a weak field. So we actually rank the ligands based on something called the spectrochemical series, going from the strongest ligand, which is on the left here, to the weakest ligand on the right. So you can see that some of these ligands like cyanide or carbonyl, nitrosyl, ethylene diamine. These are pretty strong field ligand. Water and ammonia are sort of on the stronger side, although water is a little bit in the middle. And then when you go to the latter part of the series, those are the weaker ligands right here. If you're asked a question where you have to predict the splitting, whether it's going to be weaker field or stronger field, if you're given one of the ligands at the beginning of the series, then you would expect that splitting to be more likely to be the stronger field splitting, which is the larger delta splitting. Okay. Another term that we use often to refer to this splitting is low spin versus high spin. So you might see that. So low spin refers to the stronger field splitting, and high spin refers to the weaker field splitting. Now, let's talk about how this splitting might affect the way the electrons are distributed. So again, I gave an example earlier where depending on what kind of splitting you have, right, of these 5 electrons here, you might see the one on the top or you might see the one on the bottom, okay? And because of the way those electrons are distributed, that affects magnetic property as well as the colors of the complex ion. But before we talk about how they're affected, first let's think about how some metal ions are affected. So these are all your first set of transition metal ions, which are all the 3D orbital containing metal ions, right, where all the valence electrons are located there. And this is just showing you some of the cations and how many electrons they have. Now, if you just have one electron, the splitting wouldn't affect anything in this case. If you have 2 electrons, it turns out that it's not really going to matter either. 3 also, but it really starts to matter when you have these 4 types of transition metal ions. So as you can see here, these are your chromium, manganese, iron, cobalt. Okay, so those are kind of the 4 where the splitting would really affect the properties of the complex ion. As you can see here, if I have the example that I used earlier, if I have 5 electrons, true for either an iron 3 or a manganese 2 ion, I could either distribute it as 5 separated or single electron, or I can distribute them as 2 paired electrons and 1 single electron. The reason this matters is because going back to General Chemistry 1, one of the properties we had discussed was magnetic property, right? And what we had said at the time was that if all the electrons are paired in a particular substance, ion or atom, then that substance is what we refer to as diamagnetic, which just means that if we magnetize that substance, it wouldn't stay magnetized. Okay, so this is, if you want to simplify it, you can say that the substance is not magnetic. Whereas if you have at least one unpaired electron, then the substance is what we call paramagnetic, which means that if we magnetize it, it will stay as a magnet. Now, the more unpaired electrons you have, the stronger its paramagnetism will be. So if you go back to the diagram that I just showed you with the 5 electrons here, as you can see, if I have either iron or manganese ion, depending on how those 5 electrons are split, I can have something that is relatively low paramagnetism, which is the one at the bottom here, or I can have something that's pretty highly paramagnetic, right? Because all 5 electrons are single electrons. So that actually explains how the complex ion is going to behave with respect to, again, magnetic property. And we can talk about The next one here on the right of that 5 electron one, which is 6 electrons. So if you look at that one, again, there's sort of two ways you can split it. The bottom side here is your strong field splitting, right? Because how do I know it's strong field? Because the difference in the top energy level and the bottom energy level is higher. Okay, so this delta right here is pretty high, whereas in the top one, the delta is a smaller gap. Okay, and so if you're dealing with the strong field one, then those electrons are not able to jump to that second level unless all the electrons are paired first. So that means that all 6 electrons are actually going to be paired. That's a configuration for that particular complex ion in the strong field case. In the weak field case, where the difference in the two energy levels are not that big, the electrons can actually be placed on that higher energy level without, sacrificing too much energy cost, right? So in this case, you actually have 4 single electrons here. Now, it's going to be pretty different magnetically when we're talking about these two configurations, because the bottom configuration is just purely diamagnetic, right? There's not even one single electron present, whereas the top one actually has 4 single electrons present. So that's going to be fairly paramagnetic. So that's a huge difference in the species that is formed by either cobalt-3 or iron-2 with some ligands. Okay, so that's one that you really want to remember, because that's the one that's very sort of black and white in terms of the difference in its magnetic property. Some of the other ones are not as clear cut. It's more like a gradual difference. So like the one that we saw just now, where there's 2 paired and 1 unpaired versus 5 unpaired. Yeah, you're going to see a difference in paramagnetism. But with this one right here, with the cobalt-3 and the iron-2, it's really clear. One is diamagnetic and the other one is paramagnetic. Okay, so this table here really just gives some values of delta, just to get a feel for how different combination of metal ion and ligand, as well as the charge on the metal, result in, different size gap between the lower set of orbitals, which remember is called the T2G orbitals, and then the higher energy orbitals called the EG orbitals. And you can see that it goes from something as low as like 10,000, for example. This is in wave number unit, to something that is 45,000 here. So you can see that some of these guys have either really small energy or really high energy. But the idea being that having different types of metal and ligand combination really affect the value of the energy gap between different complex ions. Okay, so this part of the note tells you that you particularly have to pay attention to that cobalt-3 complex ions that I just mentioned earlier, because that one is where there's clear difference between whether you're having the strong field case, in which case all you have is a diamagnetic species, or a weak field case where you have a paramagnetic species. Another factor that's affected is color. So the color that observed in the complex ion really depends on what color the ion itself absorb. Okay, so the color that is absorbed is the one that we don't see, and then the color that is not absorbed is the one that we end up seeing. So those colors are often called complementary colors. So here is a short list of, in the visible region, observed color versus absorbed color. So for example, if we see that our complex ion has a red color, that means it's absorbing a blue-green part of the visible wavelength, which is about 490. If we have a complex ion that is violet, that means it's absorbing in the yellow-green region, which means it's about 570 nanometers. Okay, how the color is affected again is because of that gap in the size of the delta. Okay, so if the delta is large, okay, so like the bottom part right here, which is a larger delta, is stronger field case, then for the electron to be excited to go to this level here, it has to absorb light of a lower wavelength, because remember that wavelength is inversely proportional to energy. Whereas if the gap is of the weak field type, which is a smaller gap, then it's going to absorb in the longer wavelength. And that's how we can explain colors of certain types of complex ions based on the type of energy that it would absorb. Now, we can actually calculate the energy using the wavelength. So this is just using the ideas that you learned in General Chemistry 1, keeping in mind that the energy of a photon is equal to h nu, which is the same as hc over lambda. So there's that inverse relationship between wavelength and energy that I mentioned earlier. But now that energy that needs to be absorbed is equal to the delta, which is the gap between the lower 3 orbitals, right, called the T2G, and then the higher G orbitals, okay? And so that delta now corresponds to hc over lambda, And then so if we know the wavelength that is absorbed, that allows us to calculate delta, or vice versa. If we know the delta, we can calculate the wavelength. Okay.